Hello and welcome. In this lecture we're going to be talking about mesh or loop analysis as well as super meshes. This lecture concludes the very fundamental circuit analysis techniques, and in the future lectures we will be looking at theorems that help us simplify the circuits further to be able to apply the techniques we've learned thus far. Let's go ahead and look at what is required to be able to understand the content of this lecture. So by this point you should be able to, having watched lectures 0 through 10, you should be able to apply Ohm's law to any linear circuit composed of voltage or current sources as well as resistors. You should be able to understand and determine current, voltage, and power relationships, the relationship between these quantities. You should be able to determine the equivalent resistance in resistive networks, as well as networks that are resistive but contain neither series nor parallel components. We've covered that in previous lectures. You should definitely know Kirchhoff's laws by now, and you should know the fundamental linear algebra concepts such as matrix inversion, Cramer's rule, determinants, and all of that is covered in lecture 9, so please go ahead and review that if you don't know what those are. And optionally, if you want to enhance your educational experience from these series, you should be either using the free LTSPICE that is provided in the link below, or some other circuit simulator that uses the SPICE engine to simulate these elements in the circuits. So let's go ahead and talk about the contents. We're going to be looking at some introductory terms and definitions. We're going to look at mesh and loop analysis, what it actually is conceptually. Then we're going to move on to super meshes, and very similar to super nodes in KCL or nodal analysis. Then we're going to look at some examples and take the quiz as usual. So let's go ahead and talk about the introduction section. So what is the approach we take for applying either mesh or loop analysis or nodal analysis? The idea is that we apply these techniques to linear circuits to be able to obtain various or a set of simultaneous linear equations. Once we find those equations, we can solve for voltage or current variables depending on which method we've used. So if we've used nodal analysis, we can solve for voltages, node voltages. If we apply mesh analysis, we can solve for current variables in the circuit. And having current and voltage, we can find power dissipated by an element. We can basically find everything we need for a given linear circuit with these basic electrical quantities. Then we can apply linear algebra techniques of choice to find those unknown variables of current or voltage to find a definitive value for it. And let's talk about mesh analysis steps. So to apply mesh analysis, you need to assign mesh currents to every independent loop in the circuit up to mesh n. And we will talk about exactly what that means. But similar to nodal analysis, you're going to basically apply, for nodal analysis we applied the nodal analysis technique to every node, so node 1 through n. In this case it's going to be mesh 1 through n. We're going to apply this method too. Then we're going to apply KVL or Kirchhoff's voltage law to each mesh up to mesh n, and we're going to use Ohm's law to express the voltages of those meshes in terms of the mesh currents, which we will define shortly. Then we're going to do the similar technique of finding the n simultaneous equations and finding definite values for those mesh currents. Now note that we're not going to look at any problems where there's a current source present, whether it's independent or dependent, because those are called super meshes and we will cover them later in this video. So some more definitions. So when you think of a loop, what is meant by that is that it's a closed path that is not closed path that no node is passed more than once. So what does that mean? So if I look at some abstract node or abstract loop here, you can see various nodes. Let's see. You can see various nodes here that I have defined. Now, we don't need to worry about the elements. It's just a very abstract representation of a loop or various loops that are contained within one larger loop. So if you were imagining that there's current flow across this larger loop, you would imagine that there's a current flowing from, let's say, this node up to this node, up to this node, back down to where it started. So you would say that the current flows this way. Now, this is one large loop. Now, within that loop, there are more loops. So you can look at this guy. You can say the current's going this way, current's going this way. You could choose this other loop. Let me do a different color. You could say this is a loop, or this is a loop. So you can see that essentially, when there's multiple loops like that encompassed within a larger loop, that there's some sort of distinction between any one of these sort of elemental loops, if you will, and the larger loop as a whole. And so there is a difference, and a mesh is basically a loop that does not contain any other loops within it. So any one of these, let's delete some of this, so any one of these guys, let's correct that, any one of these loops is called a mesh. So for example, this larger loop that I just cleaned up here, this would be a, let's fix that, this would be a mesh here, and so would this guy here, this would be a mesh, this would be a mesh, and this would be a mesh, and so on and so forth. So that is the difference between a loop and a mesh. So the mesh is kind of a child of a loop. You can think about it like that. And now let's talk about planar circuits and non-planar circuits. So everything we've seen so far would be considered a planar circuit. You would have your normal voltage source, some resistors, and some other element here, some current source, for example. This would be a planar circuit. You know, you could apply your KCL. Some currents are going in and out of the nodes. Now we're going to learn how to apply KVL or use the mesh analysis. Now, this is a planar circuit, but what if you had a non-planar circuit? So a circuit where it's kind of like 3D, or it's sort of in a complex fashion. You can't reduce it down to any simple planar circuit. So this is one example here where we have a resistor flowing from one end of the cube to the other end. And the trouble with that is that whereas Kirchhoff's current law, you can apply it to any one of these nodes and you could faithfully calculate the amount of current going into that node or leaving that node. You can't do that with mesh analysis because it's based on Kirchhoff's voltage law. And if you kind of imagine only, for example, this section and try to make it planar, so you can imagine I have, let's say there's another resistor here, some resistor here, here, forgot to add another one here, another one down here. It's kind of hard to see. If you imagine this, then there's another kind of resistor popping out of the screen here, the 2D screen, because I'm kind of projecting this simple circuit, one end of the one edge into the page here. And the problem with this is that you have a resistor kind of bringing energy, potentially bringing energy or current from another node into that particular node. Let's say from, this would map to this guy here. So you can imagine there's some floating resistor there that's kind of injecting energy into my circuit. And if I am to apply Kirchhoff's voltage law, you could see that conservation of energy doesn't really, by just looking at this planar circuit, you can't kind of satisfy conservation of energy because there's current coming out of that system, it's coming into the system from a different system, and you're not accounting for that system because you can't reduce this large circuit into a 2D planar circuit. And so the point is that the conclusion is that whereas you can apply KCL to any given node, even for a non-planar circuit, you can't do that for, you can't apply KVL or mesh analysis to non-planar circuits. So let's keep that in mind. Alright, so let's go ahead and look at a conceptual example that will help us put the instruction that we kind of put together in the previous page into practice and see how we actually set up the conditions for mesh analysis. So looking at this circuit, as we said, we can't have any current sources at this moment because we're not dealing with super meshes. We're just going to look at regular meshes, in which case, if you look at this circuit, we have 3 different loops. We have this loop, and also a larger loop that encompasses the entire continuous branch that you can see here that I'm tracing out. Now, for mesh analysis, as the name suggests, we should define some currents flowing inside of a mesh. So the way we do that is usually we go clockwise. So we start kind of going this way, and we kind of define a current circulating inside of this mesh here. Then we can do the same thing in the other mesh, and I'm going to label it I1 and I2. So as we said, as part of one of the instructions, we have to define some currents for the meshes. So these are called mesh currents. So we define mesh currents. Then what we always do for circuit analysis problems is to basically define a voltage drop according to passive sign convention based on previous lectures. So I'm going to just define some voltage drops. So I'm going to put the pluses here and put the minuses here. So meaning the current should flow from positive to negative, and so on and so forth. The next thing we're going to do is we're going to define branch currents. This is also important because we have to be able to relate branch currents to mesh currents. So that's another important step which I will do in cyan. So I'll call this, I'll use capital letters to denote branch currents and lowercase letters to denote mesh currents. So I'll call this I1. Call this based on the passive sign convention. I'm going to call this I2, and these are arbitrarily defined. It's okay as long as you're consistent with it's okay what you do as long as you're consistent with your own convention that you set. So these are the branch currents I'm defining. Just do keep in mind that the branch current is a current flowing from one particular node at a particular potential to another node. So in this case it's going from this node defined as VS1 into some other node. We can call it VX, for example. It's a different voltage because there's some drop across R1. I2 is going to flow from this node to through VS2, and I3 is going to go from VX through the ground node here. We can call that ground. Okay, so having done this, then we can go ahead and see how we can actually do the mesh analysis. So if you do KVL, what you'll notice is that, so how we start is I will usually start at the bottom here, go clockwise, and just look at the sign and the voltage drop or rise. So if I'm starting from here and going up according to this mesh current, I would see a minus VS1, a plus I1 times R1, because remember step 2 was to define voltages in terms of currents in the mesh analysis. So let me just go ahead and write this. So for the first equation I'm going to look at mesh 1. So for mesh 1 we have minus VS1. I'm going to see a plus sign, so I say the positive polarity is going to be I1 times R1. So I1 R1, that's the voltage drop across R1. Then the tricky part is this part. So you have to make sure you understand this. So when I see this guy, I'm going to say a plus, as always. I'm going to say a plus across R3, so nothing weird there. But what is kind of different is that the current flowing in this branch is I3, but in terms of meshes, it's going to be expressed as I1 minus I2. The way you can see that is, okay, let's look at this resistor R3. So what you have here is two mesh currents. One is going clockwise, so it would look like this, I1. The other one is going clockwise in the other loop, and what that kind of gives you is that it's going to go upwards like that. So that's I2. So if you've defined the convention, the sign convention, to be in this manner, so plus up top, minus on the bottom, what that means is that the current is going to flow, the net current is going to flow this way, which is I3. So what that means is that I3 is a difference of I1 and I2, but you have to make sure you understand what sign it is. So because we're saying because we've defined plus and minus to be in this direction, so high to low potential this way, so current must be flowing this way. There's a net current going from positive to negative based on what we chose per the passive sign convention, and so because of that, we're going to say that I1 minus I2 is going to be the net current that's going to flow this way. So it's kind of, the assumption kind of here is that I1 is greater, and so the difference between the two is going to be the current flowing downwards. Now you can change this up, but you have to make sure everything in the circuit makes sense per your convention. So if you're kind of assuming I2 is going to be greater, then your plus has to be on the bottom, minus up top, and so on and so forth. So you have to really understand what we're doing here and what are the assumptions and what is the effect of the application of these assumptions. So up to this point we should be good based on previous lectures because it's just KVL. Now going forward and writing this, we're going to say R3 because we saw positive as we were going this way, positive. R3 times I1 going down minus I2 going up. So it's going to be I1 going down minus I2. All of that is equal to 0. So this statement is a conservation of energy. It's telling me that in this loop, the there's only rises of voltage, and voltage rises and voltage drops. So if I go up, I'm going to rise by some voltage. I'm going to go across the resistor and drop, go across the resistor and drop. And so that's what this statement tells us. Let's go ahead and find for mesh 2 what the voltages are. So I'm going to go up now. Now check this out. I'm seeing a negative sign as I start this way. I'm going to go up clockwise and see a negative sign. So I'm going to immediately put a negative. I know it's going to be R3, and I have to express it in terms of the voltage has to be expressed in terms of resistance and current. So I see a minus, I see R3, I immediately put that down. Then I look in the parentheses, and let's see, the current is again I1 minus I2. So we've said that this current is I1 minus I2. So I simply put that current down. Then I proceed and I see a plus R2 multiplied by the mesh current I2. I go down and I see a plus VS2 set equal to 0. Now, as always, based on previous lectures, as engineers we need to be able to get this into matrix form to be able to solve it efficiently and quickly using some sort of a matrix solver. So I'm just going to go ahead and simplify these so you can see it better. Combine the coefficients for a given variable, so I move VS1 to the other side. That's equation 1. Looking at the bottom side here, we have let's see, I said VS2, sorry, should be VS1. It's going to be a positive on the other side. On the bottom equation, we're going to have minus VS2 as I move this guy here. I have a minus R3I1, and let's see, add to that a positive R3 because of this guy, and a positive R2 times I2. So to simplify it even further, we're going to have R1 plus R3 times I1 minus, sorry, let's put a plus here, put a minus here so it's clear what the coefficient is. I2 is equal to VS1. Then I have a minus R3 I1 plus R2 plus R3 and minus VS2. So now we go ahead and put this into the matrix, into matrix form, and what that's going to be is, let's go ahead and make this. We have the voltage vector equaling the coefficient matrix here, which is unique to this particular system and its architecture. So we're going to have, let me go ahead and write this also, I1, I2, these are my unknown vectors. And so what we have is R1 plus R3 minus R3 minus R3 and R2 plus R3. And if this does not ring a bell, you should definitely watch lecture 9 and do some practice problems there. Now what you would need to find here is that we're using mesh analysis to find the currents, the mesh currents, and so what we would do is we would apply basic linear algebra theorems. For a square matrix, you find its inverse in some manner. So what I would do is I would basically apply the inverse matrix of the coefficients, the resistor values. I would denote the inverse here, call that inverse, and I would do a matrix multiplication with the known voltage vector that are inputs to the system, and that will give you the current vectors. Okay, now let's go ahead and begin looking at a numerical example. So given the kind of the cookbook recipe given in the first example, we can go ahead and apply the same principles and find currents, the mesh currents here. So looking at this circuit, you can see there's a voltage, two different voltage sources at two different places, and there's no current sources, of course, and you have some resistive networks. And applying KVL is going to help you kind of find the element voltages. But remember that we're doing mesh analysis, and the mesh analysis kind of gives us the current for the entire mesh. And that is helpful in many ways, because once we find the mesh current, we can kind of define, or we have also found our branch currents for some of the branches. Now, for kind of the branches that are shared between two different meshes, you have to remember that the current is going to be the difference between two different mesh currents. So that's a very key point to keep in mind for problem solving sessions and exam and quiz problems. So let's go ahead and define the two meshes. I'm going to again go ahead and use a clockwise convention, because that's a very that's kind of the way people always do this. Electrical engineers do it this way. Of course, you can do it counterclockwise, but it's really just based on common sense and what's reasonable. So looking at this, then I'm going to then define voltage drops according to the passive sign convention. So I'm going to say, okay, it's going to go with I1. The voltage drop is going to be kind of reasonable here. I start with this voltage source. There's some voltage drop across R1. And then I also do the same thing here. For fun, let's do it kind of differently this time. Let's go ahead and kind of change it up here and put the minus up top. And what this does is it kind of helps us prove that nothing should go wrong if we change up our signs. As we've seen before in the KCL case, when we're doing nodal analysis, the direction of current doesn't matter so long as it's consistent within the system. So that's kind of how we define that guy. So let's go ahead and do the rest here. Make sure there are no conflicts in terms of consistency for signs. And so looking at this, there should be no problem. So kind of the assumption here is that you can see I1's flowing this way. And we can see that there's a voltage rise as I1 goes from this point to this point across that resistor. So immediately you should see that the assumption here is that I2 is greater than I1. That's kind of what that implies, because for the net voltage drop to be in this direction, I2 would have to be greater than I1 for that branch current to kind of flow that way and give you a voltage drop that is shown here. That's kind of you have to think about the intuitive notion that kind of the implications that arise from this you have to understand it from an intuitive perspective. Additionally, what we can do is, let me actually go ahead and finish this one. Now, we do have to remember there are branch currents as well. So the branch current going this way we can call I1. Branch current going this way we can call I2. And again, they have to be consistent with the passive sign convention. Now, the branch current this way, of course, would have to be going in this direction. That is I3. So let's go ahead and kind of first see what my currents are. So how do my branch currents relate to my mesh currents? So we can see that I1, the capital I1, is equal to I1 that is lowercase, and that is because they're exactly the same. Sort of the definition we've given here shows that they're exactly the same up to this node. And so what you would say is that I1 is equal to the mesh current. Now, I2 then is going to also kind of line up with the lowercase I2. And so that is going to be as such. And looking at I3 now, we can see that it's going to be the difference between I1 and I2. So you can see that I1 is flowing this way, I2 is flowing this way. And we can see that I3 is I3 is pointing in the same direction as I2. And so what you would expect is that I3 is equal to I2 minus I1, because the assumption is that I2 is greater than I1. And so let's go ahead and move to the next step and actually perform KVL. So I start here and I go up clockwise. I see a negative 10. Let's go ahead and do it symbolically first. I see a negative VS1. I continue to go up and I see a positive R1 times I1, or in this case the mesh current I1. So I'm going to have I1 R1. Then I'm going to go down and I'm going to see a plus VS2. I'm going to go further down. I'm going to see a minus sign. Very easy, procedural. Then I'm going to see a minus sign R3 times. Now you have to pay attention here, and that is the current going this way I3 is going to be I2 minus I1. All of that is equal to 0 as I come down to the same point. Now let's go to the second branch, or the second mesh, and I'm going to start down here again. As I go upwards, I see a positive sign, R3. The current again is I2 minus I1. I continue to go up and I see a minus VS2. I continue to go up and right clockwise. I see a positive sign, R2 times the current, which is I2, moving in that direction. And I continue to go down. I see a plus sign, R4 times I2 again. And I come down to the same point, set that equal to 0. And so now, if you go ahead and simplify these equations. So here's I1, the first equation. I'm going to basically move the voltages, the source function, if you will, to one side of the equation. And so we have VS2, let's see, VS1 minus VS2 actually should be the, so what I've done is I've taken these guys to the other side. That is equal to, let's simplify this, so we have R1 plus R3, R1 plus R3 times I1. Then we have a minus R3 times R2, I2, minus R3 times I2. That is the first equation. The second equation, I move again VS2 to the other side. VS2 is equal to, let's simplify I1. So let's see here, I1, there's only a negative R3, I1 plus, let's look at I2. So we have a R2 plus R4 plus R3. So R2 plus R3 plus R4 is I2. So having found this, we can put it into matrix form. So all of this simplifies to VS1 minus VS2 all of that is equal to the coefficient matrix minus R3 minus R3 now that's going to be I1, I2. Alright, now let's go ahead and plug in the numbers and find the inverse matrix using MATLAB. Okay, so I went ahead and plugged in the numbers for all the resistors based on the schematic, and having simplified them, you get the voltage vector 5, 5 and the coefficient matrix as you can see below. And so plugging this into MATLAB, because we already covered linear algebra fundamentals, we go ahead and go to MATLAB. You can see the simple script I wrote here. You basically input V and A and then find the inverse of A, which is the coefficient matrix, the inverse of the coefficient matrix. Then we multiply the inverse by the voltage vector, and I'm declaring the first current and the second current here. And what you can see is that the values are 0.783 and 0.675. And I've rounded those up to the third decimal place. And now going into LTSPICE, so what this did is it basically helped us find the answer to the matrix equation that we found. So MATLAB does not know anything about anything that has happened up to this point. So all it's doing is just doing linear algebra for us. Now by using LTSPICE, then we can kind of check our kind of the circuit setup and make sure that we got the right values. So I've gone ahead and basically set the circuit up, and I'm going to go ahead and run a DC operating point, as you can see here below. So I've gone ahead and simulated it, and what we want to pay attention to is the current through R1 and the current through R4, which are the mesh currents I1 and I2. So looking at R1, we can see we have a negative 0.783, and for R4 we have a negative 0.675. Now the magnitudes are correct, but the sign is negative. Now can you go ahead and stop the video and try to guess why the sign is negative. So assuming that you've kind of guessed at it and kind of made a conjecture, the reason is that the way the SPICE netlist is defined is that, let's go ahead and look at the netlist. You can see here that with this being node 1 and this being node 2, R1 is defined as, it starts with node 2 and then node 1. And so the direction in which it's set is going to reverse to what we've defined the current to flow, the passive sign convention basically. And so that's why you would get a negative number, is that it's kind of assuming that plus is here, minus is here, current's going in this direction conventionally for this element. If you go ahead and flip this resistor 180 degrees, you would see that the minus sign would go away just because of the definition of this element. And so you have to always be able to check your answers and not get, not panic about why an answer is what it is. So let's go ahead and move on to the next problem. Okay, looking at the third example, we have 3 loops now, and we have a dependent voltage source that depends on the current I0 flowing through R1. And so we're asked to find that particular current I0, which then which kind of requires us to know every single voltage across every element. So let's go ahead and kind of review what we need to know and what we need to apply to the mesh analysis problem. So we know that we can use clockwise or counterclockwise currents so long as we're consistent with all of the consequences that follow. So for example, if I say that I1's flowing in the clockwise direction, then the direction in which then I need to kind of consider how that affects the direction of branch currents. For example, the branch current I1 here that's flowing in this direction, and also the resistor currents flowing through the resistors, and basically how I1 and I2 kind of fight each other to get some current flowing into this branch. So as long as we're consistent with whatever kind of declaration we make here, all the math should work itself out. So looking at this problem, then I'm going to just go ahead and start writing the well, before writing the equations, we're going to assign polarities. So for R1, I'm just going to go ahead and assign a common sense polarity. So I'm going to have plus here. For R3, I'm going to say any direction is fine as long as it's consistent. Let's put the plus there, put the plus there. Now put the minuses in these locations. And so we just have to make sure we're consistent. Nothing here is kind of breaking any rules for the system. So having done that, let's go ahead and actually solve for the first mesh. So I'm going to again go up and see a negative Vs because I see the minus sign first. I'm going to go up and get to the plus side of R1. The current I'm going to see is going to be I0, so let's go ahead and just declare that first. Call it I0 first and then find more variables for it. So that's going to be I0 plus, because I see a plus here, I'm going to see a plus R4 times, we're going to have I1 minus I3 now. As you can see, I1 goes down, I3 goes up. So I'm going to have plus, let's take that out. I1 minus I3. Let's go ahead and write the equation for the second mesh, and that is going to be, let's start here by the minus side of R1. So I'm going to say minus R1 IO. Then I see the plus sign of I2. That is the mesh current I2. I go down and I say a negative terminal of R3. That's going to be I3 minus I2 because I3 goes this way. It goes with the voltage drop and I2 goes against it. So it's going to be I3 minus I2. Let's clean that up. 3 minus I2. Then for the third mesh, we're going to start down here. We're going to see a minus R4 because of the minus sign. Now the current's going to be I1 is going to flow with the convention, passive sign convention, and I3 is going to go against it. So it's going to be I1 minus I3. I1 minus I3. Then we're going to have, we're going to see a plus side as we go clockwise, plus sign of R3 times, so we have R3 going with the flow and I2 going against it, so that's going to be I3 minus I2. Then we're going to continue and go here and see a positive 5IO is equal to 0. So I'm going to go ahead and just simplify these equations. Well, before that, let's go ahead and write a fourth equation relating I1, I2, and IO. So IO is going to be the difference between, so I1 is going to flow this way, I2 is going to flow against it. So that's going to be I1 minus I2. So I'm going to go ahead and simplify these equations into matrix form. Okay, one point is that I forgot to add equals 0 for these two equations, but other than that everything is correct. So if you followed along up until how we found these four equations, then the rest of the simplification should be easy. So for the rest of the simplifications, I basically move the voltage vector to the other side, the voltage here to the other side, and basically simplify everything in terms of coefficients being multiplied by I1 and I2 and I3. And so the way I did that is I plugged in IO into this part of equation 3 and this part of equation 2. And by doing that and basically double checking my signs and making sure I do it very carefully, you basically can check your work against mine here and get it to this equation here, and then finally put that into a matrix form and add all of the values from the schematic into here. The next step would of course be to solve this matrix in any way that you like. So I use MATLAB to quickly find the inverse and multiply it by the unknown matrix. So remember that AX is equal to B is the way we do this. So in this case, the X vector would be our current here, and A would be this matrix. So this would be our AX equal B. So the way we solve this is we take the inverse of A and multiply by both sides. It's a matrix multiplication by both sides. And do note that it matters how you multiply matrices, so you can't just kind of change the order of where you can't multiply B by A inverse. It has to be A inverse times B. So otherwise you get a completely different answer. So A inverse times A would give you the identity matrix, which is just diagonal ones. So that you can just ignore that, and that will be X hat, or X, the X vector is equal to A inverse times B. And so basically if I just multiply, in other words, my X, which is my I, the currents, would just be the inverse of A, the inverse of this matrix, multiplied by B here. And when I do that in MATLAB, you can see, if I simply write a script here to do that, you can see all the values, I1, I2, I3, and I've written those down, and you can see I out, which is the difference between I1 and I2, is 1.615. So if I go back here, you can see that's what I've written down. And again, MATLAB only performs this calculation without any knowledge that where this came from. So this could be circuits, this could be any other field of engineering. So what we need to do is look at a circuit solver. In this case, I'm using LTSPICE again, and I'm gonna run it and look at the current through a VO, which is my voltage source that is of 0 voltage. Basically, the reason I have to put this in here is because I have a current controlled voltage source, and so basically it's going to take the value that is the current that is going through the current that's going through this voltage source, and it's going to multiply by 5, and that's going to be the voltage across that source, that dependent source. So that's the reason that I have this sort of dummy voltage source here. It does not change any voltages because it's a voltage of 0. So looking at that, you can see that the current through it is 1.615, and the way that was obtained is the current I1, which is going through V1. So if you look at I of V1, we get negative 1.807, which means the current's flowing in this direction, and that is, if you subtract that by the current through R2, which is 0.192, if you subtract those, you would see that the magnitude is the 1.615, which is what we have found. So we can now move on to super meshes. Let's go ahead and discuss the idea of a super mesh. So what we've dealt with so far are cases where there are only voltage sources and resistors in a given circuit, and so the mesh currents are simply currents that are passing through voltage sources and resistors. And if you recall, for a voltage source, it will give you the necessary voltage, the defined voltage, no matter what the current through it is. And so that is not a problem for KVL or mesh analysis. Now, if you add a current source, that is where things get kind of tricky. So, and the reason being that the voltage across a current source is not known. The voltage will vary to whatever value it needs to be, such that the current that is defined, let's say for example 2 amps, that current source will provide 2 amps no matter what the voltage across its terminals are. And so with mesh analysis being a method that defines voltages, you can see why that is problematic. And so the way we deal with that is we kind of separate them into two cases. So for the first case, the problematic current source is kind of only affecting one of the meshes. And so in this case, if you look at case 1, this current IS is only affecting the mesh that is defined by I2, is characterized by I2. And so what we do in this case is we simply, depending on the signs of the currents, we set them equal to each other. So we know that whatever IS is simply going to be, the magnitude is going to be I2. Now the direction is opposite to I2. So what we would say is that to solve this problem, we would say I2 is equal to negative IS. You can see, hopefully that is apparent. So I2 is defined this way, IS is going opposite of it, and therefore they're the same magnitude but opposite value, opposite direction. Now looking at this other case where the current source sits in between two different branches, the way we would solve that is we would first ignore the problematic branch. In this case, this is a problematic branch because it has a current source, so we ignore that and we do a simple KVL as we normally would. So we would find, so if I do KVL, I would find negative Vs, let's say directions are this way, plus R1 I1 plus R2 I2 plus R4 I4 is equal to 0. So that is the first thing we do. Now remember, we need two mesh currents, I1 and I2, and so what we do for the next step is that we know we're going to need two equations for two unknowns, I1 and I2. Sorry, I made a mistake here. So R4, let's see, this should be, right, this should be I1, R1, R2 I2, and R4 I2 as well. So what we do next is that we apply KCL to this node, and looking at the directions, I1 is flowing this way, so that will be that direction, I2 is flowing this way, and this current that is coming up IS is flowing this way. And so what we would get is that I1 plus IS is equal to I2. You can see the directions here, I1, I2, and IS. And so given these equations, then we can find, you can see we can relate I1, I2. This is some constant, is a given, so we have I1 and I2 in two different equations, and we can find our desired I1 and I2. We can find values for it. So this is very similar to the super node example. So anytime you see a super mesh, basically just ignore that problematic branch, simplify the loop, take these out, simplify the loop, and then at the very end apply KCL to it to find that, to relate that problematic current to the mesh currents. So let's go ahead and look at an example. Okay, in this example we're asked to find all of the mesh currents. So we're going to go ahead and actually define the mesh currents according to our own whichever way we like it. So I'm going to say this is I1, this is I2, and this is I3. So right away we can see that we have a problematic branch. We have a super mesh, and the super mesh is in this branch. So right off the bat we know that we have to ignore it initially. And so again, before we actually do these things, let's go ahead and define polarities for our resistors. Okay, so let's go ahead and ignore this branch and just assume, kind of imagine that our loop is the way I've traced it here. So going forward then, we have to, now here's another key point, is that when you ignore this branch, you can't just say that I1 is the one flowing through R2, for example. You have to still use the same current that was defined for that particular mesh. So even though we ignore this branch, we still use I3 to define the voltage across R2. So let's go ahead and start here and go clockwise. So I'm going to go up and see a negative, so let's say KVL. I'm going to go up and see a negative VS. I'm going to go here and see a plus R1 multiplied by I1 is going this way, I2 is going that way. So I'm going to say the difference between the two, I1 minus I2, is going to be the current. Again, the reason we do I1 minus I2 and not the other way around is that the passive sign convention tells us that the current must be flowing from positive to negative, and so the only way that can happen is that if the assumption of I1 being greater than I2 is true. So we're going to assume that, and if that is incorrect, the mathematics will take care of it, so long as we're consistent. So I1 minus I2, we're going to continue to go, and we're going to see a I3, we're going to see a plus I3, sorry, let's do it the right way, do it the conventional way. I'm going to say a plus R2. Now the current is going to be I3 minus I2 for the same reason, so I3 is going in the same direction as the passive sign convention, so I3 minus I2. I keep emphasizing this because it can be tricky when you first see this concept. So I3 minus I2, then we finish off with plus R5 times simply I3, and all of that is equal to 0. Now let's consider the problematic branch and apply KCL. So we know that we have IS leaving this branch. We have I1 minus I2 coming into this branch, and we have I3 minus I2 leaving that branch. So looking at those, we're going to have I1 minus I2, which is this guy. That's going to equal these two currents that are leaving, so IS plus I3 minus I2 minus I2. And so what does that do? So I3 minus I2, so we can see that these guys cancel, and we have I1 is equal to IS plus I3. So we have here we have two unknowns. Here we have, of course, 3 unknowns. So we're going to need one more equation. And of course, we're going to get that equation by analyzing the second mesh, which I haven't done. I should actually move this down and actually finish up the second mesh before doing the KCL. So having done this, we can just leave it down here and just do it for the second mesh. So for the second mesh, let's start at this side because it's easier if you see a plus sign. So I'm going to have a plus R3 multiplied by I2 going down there. I2, then I'm going to go here and see a negative sign clockwise. I'm going to see a negative sign R2. Then I know the current is I3 minus I2. I3 minus I2. Then I'm going to go here and I'm going to see a minus R1 times I1 minus I2, all equal to 0. Let me go ahead and move this back up now. I need some space. And we're going to go ahead and actually, so now we have 3 equations, 3 unknowns. So let's go ahead and solve or move everything to one side and then have only coefficients times the currents. I'm going to go ahead and stop the video and do that. Okay, so as you can see here, I've gone ahead and simplified equations 1, 2, and 3, and basically gotten everything in terms of the sources to one side and the currents kind of separated as I1, I2, and I3, and as well as their coefficients. I've then plugged them into a matrix and simplified all the values to get the matrix below, and applying, doing the same thing with MATLAB and basically running this simple script here. I get the values for I1 and I2 and I3 as you see that I've written them down here. Now again, this MATLAB only verifies this equation, so up to this point, getting everything up to this point and getting these values only tells us that our equations have been done correctly, but setting them up correctly is the circuit part of things. So the math alone was done by MATLAB, but we're going to use LTSPICE to actually verify if we've set the relations of each component to each other correctly in terms of voltage and current. So looking at this, we can see that the current I1, let's move this to the side. So looking at I1, which is the current through this, basically this voltage source, we're going to see that the current through V1 is negative 5.99 amps. And of course the magnitudes are the same, but the negative sign simply means that it's not going, this voltage source is not sourcing that current, it's sinking that current. So the current is actually going counterclockwise in that mesh. Now I2 is the current flowing through R3 to be specific, because everywhere else is kind of, this mesh current is kind of mixing with different meshes, so this is the only element where only I2 alone flows through R3. And so if you look at R3, the current through it is 4.05, which matches what we calculated. So the mesh current is indeed going in this direction, the clockwise direction. For I3, that is the current going through R5, and it is 0.99 amps, which is what we have here. And I3 is also going in this direction clockwise. So the only current that we should change is the direction of I1, which is going in the opposite direction. So having seen all these examples, we can go ahead and take the quiz now and move on to the next lecture. Okay, so for the quiz, we're asked to find all of the mesh currents. You can define it any which way you like. Remember to be consistent when you select a certain mesh current. And you're given that all of the resistors are equal to 1 ohm. So what we need to do is find the mesh currents, and so we're going to apply the same method we've done so far. Please go ahead and stop the video and give this a try before you watch me solve it and verify it with MATLAB and LTSPICE. Okay, so assuming that you've stopped and tried this, I'm going to go ahead and solve it. So I'm going to go ahead and give these mesh current variable names. I4 and I5. Next thing I'm going to do is basically assign directions. I'm going to say plus, plus, plus. Again, this is arbitrary so long as you're consistent. Now I'm going to go ahead and just write all of my equations. So let's go ahead and do all of our KVL equations. So we have 5 unknowns. We're going to need 5 equations at least that are unique from each other, linearly independent from each other. So starting from here, I'm going to say positive R1 times I1. I'm going to go to the right and see a plus R3. And then I'm going to have an I1 minus I3. I'm going to continue to go and see a plus R2, sorry. It's going to be I1 minus I2. Hopefully it's clear by now. Looking at the second mesh, I'm going to start here and see a negative R2. The current's going to be I1 minus R2. Or I2, sorry. Then I'm going to go ahead and see a plus R4. current's going to be a I2 minus I3. Finishing up this mesh, I'm going to say positive R5. It's going to be a I2 minus I4 equal to 0. I'm going to move on quickly to the third mesh. I'm going to start here. I'm going to see a minus R4 times I2 minus I3. Continue to go up, see a minus R3 times I1 minus I3. I'm going to go here and I'm going to see, I'm not going to know the voltage across this this component, but what I do know is that whatever I3 is going to equal the negative of IS. So I will say that at the very end. So I'm going to say this is a plus Vx, for example, plus Vx. And let's see. So I started with I4, go there, and see a plus R6 times I3 minus I5. And set that equal to 0. Then I'm going to go to, let me write this kind of auxiliary equation here. The fact that I3 is minus IS is equal to minus 5 amps. Let's keep that in mind. Go to the fourth mesh. Now here I'm going to see a minus Vs. I'm going to go up and see a minus R5 times I2 minus I4. Then I'm going to go ahead and see our positive R7 times I4 minus I5 is equal to 0. Then for the fifth equation, I'm going to start here and see a minus R7, I4 minus I5. I'm going to go up and see a minus R6 times I3 minus I5. And all of that is equal to 0. So what I'm going to do now is go ahead and find the unknowns, or simplify the equations. So having simplified the equations and essentially ignoring equation 3 because there is a Vx, which is a voltage across the current source appearing across it, I essentially ignored it because we have an additional equation, which is what I'm calling equation star star, and that is that I3 is equal to minus IS, or minus 5 amps. So going ahead and basically untangling all of these equations and writing them in terms of the source equal to the some coefficient times the current vectors or variables, you essentially get these equations. I'll let you stop the video and check these for your own against your own work. And now recall that all the resistor values are 1 ohm, so that really simplifies our algebra or arithmetic. So another key point is that you can represent equation star star with this, so you can say negative 5 is equal to basically zero out every other variable except for I3, which we put a 1 to it, multiplied by 1, and that's essentially the same, kind of like the linear algebra representation of that equation. So doing that and plugging everything in, we get this matrix. Now I've gone ahead and plugged it into MATLAB. I'll show you the script as well. So here's the script to find the currents. You can see the values here, I1 through I5, which I've gone ahead and copied down on the bottom. Now here are all the values, and looking at LTSPICE, I've set her up in this manner, and I actually copied it into this page so we can just look at it easier. So this is a little bit tricky to verify because of the interdependencies of all these meshes. You basically have to do some manual branch current calculations. So for example, because SPICE doesn't LTSPICE doesn't directly tell us the mesh currents, and so because we have mesh current equations here and all these variables are simply mesh currents, we have to do some manual calculations. So I start with a node that where the mesh current is the branch current. So for example, this is a perfect candidate because you can see that the the branch current going through R1 is actually that mesh current as well. So we can see that I1 is equal to negative 1.94, and verifying here we have a 1.94, which is in the opposite direction, and so that's why we have a negative sign. It's going against the mesh current here. Now looking at the current through R2 now, we see negative 1.11 amps, and essentially the way we can verify that is that the way we define them. Let me go ahead and show the polarities as well. Okay, so I've also added the assumed polarities for the resistors. So the mesh currents as well as the resistor polarities are what we assumed from the get-go. So looking at these, we can see that the current 1.11 amp through R2 is going opposite that, opposite the passive sign convention, and so we would expect a negative sign there. Now, in the case of the first resistor, we have a positive value in LTSPICE, but we have a negative value from MATLAB. We'll get to that once we analyze everything else, because we're going to see how those directions kind of affect every other current. So in this case, IS is going down, but it's a negative 5, so essentially that's 5 amps going. That's 5 amps going in this direction, which is what the original situation was. Let's look at. So we verified R2. Let's do this. Let's check mark it. We have verified R2. Let's look at R3. So we have. I'm going to need to look at V1 minus V2 over 1, which is just V1 minus V2. V1 minus V2. So that's 8.88 minus 11.94. That's the direction we've assumed. Sorry, let's look at that. So that is the opposite. I was looking at this guy. So this is plus minus. So actually, it's going to be V2 minus V1 is what direction we assumed. So V2 minus V1 is going to be 11.944 minus 8.88. Basically, it's going to be 3.05, and that's going to be going in this direction. But we get a negative sign here through R3. Let's see here. So with this guy being plus, it tells us that our assumed direction was incorrect. Let's see here. What do I have? So okay, this agrees because let's go ahead and write the LTSPICE one. LTSPICE results in purple. So LTSPICE is telling us that the current through R2 is gonna flow opposite. Now here's where it gets confusing, is that the nets list is defined, it kind of defines resistors at the end point and then at the initial point, and so there's a negative sign associated with that as well. So that's where the sign gets confusing. But kind of following the magnitudes, you can see that for R3 we have 3.055 going in the direction where there's V1, V2. So from V2 to V1. So V2 to V1. That's where that would go. And let's go back to R2 again and look at that negative sign. So we would check it by VS and V1. So VS is 10, V1 is 8.88. So LTSPICE would be telling us that current is going to flow in this direction, which is agreeing with the MATLAB calculation, as you can see here. And here it also agrees because that's a negative sign. The MATLAB calculation says that the current through R3 goes to the right, and it's a negative sign though, and so the LTSPICE kind of tells us the correct direction in this way. But I3 is the mesh version, so we have to keep that in mind. So we can't just kind of mix up the branch and the mesh currents. Now let's look at this current here. So V1 minus V3. V1 minus V3 would give us something like 4.11166, and that's the branch current we have going there. Now let's see, how can we verify the mesh currents? So we said that in this case it would be I2 minus I3. I2 minus I3 would be this current. We kind of need multiple variables to verify this. And so let's say I2 minus I3 is equal to 4.1666 amps. So that's one thing to keep in mind. It gets a little bit kind of confusing to look at all this. So next one is let's look at R5. We have 10 volts minus V3, which is 4.77 over 1 is going to give me 5.27. Now looking at the current through R5, we see about the same current as expected. Let's see how we can figure out the mesh from these. That's the ultimate challenge here, is to find the mesh currents from the and compare it to LTSPICE. So I4 minus I5 should give us 4.722 amps. I'm going to go ahead and find all the conditions so we can see what we can do. Okay, well, remember that the key to relating the mesh currents that we have assumed and calculated for, and to relate that to the LTSPICE branch currents, we essentially have to rely on R1, because that is the only resistor where the mesh current is equal to the branch current. And so that first relation up here, which is that I1 minus I2 across R2 or through R2 is equal to 1.111, and so using that relation we have to solve for I2, and I2 then is going to be our actual mesh current, and that is if I take it to the other side, I have I1 minus 1.111, and I1 was about 1.944, so 1.944 is 1.111. Let's see here, I have a negative sign. It's going to be a 0.833. However, what I'm going to do here is to stop, because it's going to be very cumbersome, and this video is going to take much longer than intended if I am to verify all of these equations. And so what I would recommend is, if you check every single one and you don't find the right answer with the branch currents and the mesh currents, I would just go back and verify all of my signs for the matrix and make sure that I have applied the equations correctly and looked at the signs correctly. That's the only way you would have made a mistake on these numbers. So with that being said, I'm going to end this video. I hope that you've gotten the main points about mesh current and super meshes out of this video. Thank you, and see you in the next lecture.